Okay, so for FRQ number 3, we have a ring that has a mass of m and a radius r, and its rotational inertia is given to be mr squared. And this ring is initially sliding across a surface without friction in the beginning at a constant velocity of v0. Later is going to encounter a surface with friction, and it will start to rotate, but it will still be sliding. After traveling a distance of L, the ring will stop sliding and will just be rotating. So part A wants us to use, well, there are two parts to part A, and it wants us to use Newton's second law in either translational or rotational form to derive differential equations that can be used to solve for the magnitude of the following, which is, so part I wants us to find a different differential equation for linear velocity of the ring as a function of time. Okay, so to do this part of part A, I'm going to use the translational form of Newton's second law, which is total force is equal to mass times acceleration. Okay, so in our case right here, the total force acting on this ring before, when it reaches this point is Fk. So that is and it is opposing on the direction in which the ring is traveling, so it will be negative. So my force is negative Fk, and that's going to be equal to mass times acceleration. Now Fk, I know is going to be equal to mu k times mg. So I can substitute that in for Fk. So I got negative mu k mg is equal to ma. Now I can cancel out my masses, and this leaves me with mu kg is equal to a. Now we want to have a differential equation for linear velocity as a function of time. So I can express my a in terms of v and t. So a is the change in velocity over the change in time, which is also the same as dv over dt. And I can substitute this into my equation to write my differential equation. So substituting this in for a, I'm going to have dv dt, that's a, and that's going to be equal to negative mu k times g. And that is the equation I'm looking for. All right. The second part, part A, wants us to write a differential equation that can be used to solve for the magnitude of the angular velocity of the ring as a function of time. So in this case, I'm going to use Newton's second law of rotational form in rotational form, and that's going to be using torque. So total torque is going to be equal to the total force that is perpendicular to the moment of arm times the moment of arm, and that's also going to be equal to the moment of inertia times alpha. Okay, so in my in my case right here, or in this problem, my total force that is perpendicular to the moment of arm is Fk. Moment of arm is r still, and I'm going to substitute my moment inertia in, which is mr squared, and that is, and alpha stays the same. So at this point, I can cancel out all my r's and substitute in fk. So canceling out one of the r's, I have one r left on this side, and I can substitute in fk, which I know is up here, is mu k mg. That's going to be equal to mr times alpha. Right now I can also cancel an m, so I'm left with mu k g is equal to r times alpha. Okay, I want to isolate for alpha, so I'm going to divide r over. So mu kg divided by r is equal to alpha. Now the reason I want to isolate alpha is because I know that alpha is a change in angular velocity over the change in time. So essentially d omega over dt, and this is this I can sub in to make my differential equation. So subbing this into for alpha in here, I get d omega over dt is equal to mu k times g divided by r, and that is my differential equation. Okay, part B wants us to derive and not solve an expression for the magnitude of the following as the ring is sliding and rotating. So there are two more parts. Let's see. We're supposed to derive an expression for the velocity of the ring as a function of time. Okay, so to derive velocity as a function of time, I'm going to use this equation, and that is this kinematic equation. V is equal to vi plus acceleration times time. Now in this problem, my vi is v0, and my acceleration I found up here, or I've isolated before, is equal to a negative mu k times g. So I can just substitute that in and I'll get my equation. So v is going to be equal to v0 plus, oh no, it's going to be minus now since I have a negative right here for mu k. So negative mu k g and then times t. And that is my expression. Okay. The other part asked me to write an expression for the angular velocity of the ring as a function of time. So similar thing to what I'm gonna do here, but with angular form now. So my equation that I'm gonna use is omega is gonna be equal to omega initial plus alpha times t. Now I know that the ring was initially not rotating, so my omega initial is equal to 0. My alpha, or my angular acceleration, I found up here is equal to mu k times g divided by r, and now I can just substitute it in to get my equation. So my omega is equal to 0, so this cancels out, and it's just mu k times g times t over r. Those are my equations. Okay. Hello. Sorry, my phone ran out of battery, so I had to charge it real quick. Anyways, for part C, we are asked to derive an expression for the time it takes for the ring to travel a distance of L. Now, the essential thing for deriving this expression is to know that before the ring has reached this point, its velocity is not equal to its radius times angular velocity. Before any of these times right here, that expression is not true. But when it does reach this point, it's going to be true, and I can use that to solve my to write my expression. So see when ring stops sliding. So when it reaches the third phase, V is going to be equal to the radius times omega. Okay, so in part B, I've already defined my V and my omega, so I can just plug them in right here. So V is V0 minus mu k times G times T. R stays the same, and I'm substituting all of this in for omega, which is mu k times G times T divided by R. I can cancel out the R, and right now I can see that, oh, this is V0 by the way. I can see that this term is alike with this term now, so I can just add this term over to combine them. So doing that, I'm going to get V0 is equal to 2 mu k times G of T times T times T. Okay. Again, the problem asked me to find time, so I'm going to divide all of this except time over to this side. So my T is going to be equal to V0 divided by 2 mu k times G. And that's my answer, or my expression. Okay. Now part D wants us to derive an expression for the magnitude of the velocity of the ring immediately after it has traveled a distance of L. So I've already found the time that I need for the ring to reach L. Now I can use that to help me find the velocity at that time. So for this part, I'm going to use this kinematic equation. No, I'm not going to use the kinematic equation. I'm going to use what I've already found up here. So, which is V is equal to V0 minus mu k times G times time, as I found up here. So now I'm going to substitute time in for T. I write all this in for T. So V is going to be equal to V0 minus mu k times G, and here's the substitution. V0 divided by 2 mu k G. Now there's lots of cancellation you can do. So mu k cancel out with mu k right here. G can cancel out with G right here. And so what I'm left with is, so V is going to be equal to V0 minus V0 divided by 2. So these two terms are alike, so I can subtract them. So V0 minus V0 divided by 2 is V0 divided by 2. So my velocity is going to be equal to V0 over 2. That is my answer, or my expression. Okay. Part E. Part E wants us to derive an expression for distance L. Okay. So to derive this expression, I'm going to use this kinematic equation. Delta x is going to be equal to Vix times time plus 1/2 times the acceleration ax times t squared. Now my delta x is L, and this is what I'm trying to solve for. Vix is V0 I'm going to substitute all of this in for time. So v0 divided by 2 mu kg plus 1/2 ax. Ax is, I've already found up here, is negative mu k times g. So negative mu k times g, and my time once again is this, so v0 2 mu k g squared. Okay, so now I'm going to try to reduce all of this. So this first term, I can combine the v0 to make v0 squared. So v0 squared, sorry. So v0 squared divided by 2 mu k g. So that's my first term. My second term, that's going to be equal to, so I can bring out the negative from the mu k, negative, and then mu k times g divided by 2, and I'm going to square every term in this in parentheses. So I got v0 squared times 4 mu k squared g squared g2 squared g squared. Okay, so right now I can cancel out a lot in this term. I can cancel out mu k, leaving me with mu k on the bottom. I can cancel out a g on here and leave me with another g at the bottom. And so what I'm going to be left with is, well, it's going to be equal to, so this whole thing stays the same. And all of this is going to reduce down to, so I have a v0 squared left. 2 and 4 combined to make 8. And I have a mu k g left at the bottom. Okay, so at this point, these terms are very alike, except that their denominator is slightly different. So what I'm going to do is I'm going to multiply this term by 4 over 4, or essentially just 1, making it still the same. So if I do that, I'm going to have v0, 4v0 squared divided by 8 mu kg, and then rest minus v0 squared divided by 8 mu kg. Now these terms are alike, I can subtract them. So this subtract this is going to be equal to 3v0 squared divided by 8 mu kg. That is my answer.